My name is Chao-an. I'm from Chao-an University in Taiwan, not in Beijing. So one has to be clear about that. I don't know how many of you visited the Calculator Museum on Monday night. Yeah, I think one of the guide indicated like the counting of numbers. And if it has three in Chinese, this is my surname. We have two words, it's forest. One word is a tree, two words forest, then three, it's a jungle, for example. So you say that in the olden days, the Chinese cannot count more than three. So we have, but now my surname is Li. So today I'm going to present what we have been doing, try to pull our program on GPU. And before that, okay, this is contents of my presentation today. I'm not really a computer scientist, but I'm going to give you some introduction, what is GPU and what is the limitation of the numerical scheme can be done or cannot be done on GPU. And later on, I'm going to introduce the three methods we have been using for the past few years, the Lady Boltzmann, Euclid compressible scheme, and the focus of the present presentation is like the projection method using multigrid to solve the pressure Poisson equation. And this is the two results I'm going to show. And you can see that the dramatic performance of GPU, I've seen this before, so why not put our program on GPU? And in my lab, we have a P100 and V100 at A100, H100 is behind the past CFD 2024. They are too expensive, so I cannot use that. I don't have the machine. But you can see that if you can port your program using GPU, that will be an advantage. So if you see this one, a copyright from the CUDA programming guide, and this is the CPU executing few tens of these threads in parallel. And the advantage of CPU, it has a lot of cache and much better than the GPU. GPU, it has a lot of threads, but the performance is much slower. And the cache size is much low. So it stands on its own. So if your method actually is explicit, then that would be better too. But you need to modify your scheme to be to run on GPU. So all the thread can access to the global memory within each block, and it has own register or local memory. But within the block, they can be communicated through shared memory. So that is the bottleneck. If your method is implicit, you need to get access to global memory. Of course, you can use a shared memory, but the size of shared memory is quite small. So the implicit method actually is not very applicable to GPU. So our first step is like we are using the Lady Boltzmann. We have a collision and all the streaming, and this is the multi-relaxation time Lady Boltzmann method. And you can obtain your density and your momentum just by adding all the distribution functions all together. And there are two disadvantages of the Lady Boltzmann method. The first one is we need to use uniform mesh. The second one is that, for example, to three-dimensional flow, you need to have 18 directions or 19 directions or 27 directions of distribution function. So in order to obtain your density and your momentum, so actually memory requirement is very high. But nonetheless, we managed to use block mesh refinement to calculate turbulent channel flow up to Reynolds number 600, IE tau 640. We have completed IE tau 1000 now. But you can see that Lady Boltzmann actually can generate very good results regarding the turbulent intensity and also mean flow velocity profile. And we also managed to calculate turbulent flow within the periodic here, and this is a really typical benchmark, and we use some kind of immerse boundary to do that, so the result seems to be okay. And this was done about 10 years ago. The Lady Boltzmann scalability of Lady Boltzmann is quite good. Now, we gradually move on to the Navier-Stokes part. So we have to choose how we coupling the velocity and pressure. And there are many ways. Artificial compressibility method, kinetic reduced local Navier-Stokes equation, entropy dam artificial compressibility method. The one we are using is the general pressure equation. So we solve the pressure evolution equation instead of solving the pressure Poisson equation. And that is that we can that is fully explicit. We use third order explicit Longy-Coulthard method. And the main problem for this approach is that we have a speed of sound. So actually, in order to obtain respectable divergence-free condition, our Mach number has to be very small. And we have been applied that to calculate turbulent dark flow, and the results seem to be quite good. And also calculate two-phase flow, and that is very good. But as I said before, the time step restriction because of the speed of sound. So actually, the time step has to be very small. So, but anyway, we can still do decent simulation out of it. Now, moving to the incompressible projection method. That is the method that we have been used for many years. So we have the momentum equation and projection method with different steps. And in order to obtain a divergence-free condition, we need to solve the pressure Poisson equation here. And actually, this is most time-consuming. And traditionally, you can use GM-ray, multigrid, whatever you use that. You can solve that. There's no problem. So how can we port that to GPU? So in order to obtain explicit method, so we have pseudo time here and the physical time. So we use dual time stepping method. This is very similar. So, but we put a diagonal term to we put a diagonal term to the pseudo time there, and this is although it's explicit, but however the Jacobi iteration, the convergence rate is really low. So actually, we try to use multigrid to accelerate the speed. Okay, now we use V-cycle. We have fine grid, medium grid, and coarse grid. Okay, for example, 8x8, 4x4, and 2x2. Okay, now we have restriction and prolongation. So now we know that if you can reach the closest level, you can see that depends on the mass size. I think this is 512 cube, something like that. So you can see the speed up. It can up to, if based on work unit, you can 6,000 times speed up compared to just one level of multigrid. Okay, non-uniform mesh actually has a slow performance, but nonetheless it's quite decent compared to this is based on one, and this is we have about 5,000 times speed up. Okay, now. So now, but if we use multiple GPUs, say for example, we have 32 by 32 by 32, and we have one GPU, you can have 5 levels. There's no problem, right? 16 cube, 8 cube, 4 cube, 2 cube. But however, you have 4 GPUs. So in each GPU, you have 32 by 32 by 8, then you only have 3 levels. But based on the previous one, if you have more levels, your convergence rate is much faster. So one possibility is you get all the other nodes. So now you get all neighboring CPU, then become this one 8x8, 4 cube, and 2 cube. So it can remain the maximum level is 5. But however, from this on, you don't have parallel efficiency anymore because all the GPU are doing the same thing at the same time. But nonetheless, the efficiency you gain by increasing the level actually is much better than the degradation of the parallel efficiency. So now this is the test case. It's a laminarly driven cavity flow at a 10 physical time step from quiescent field. And you can see that at different grid size, actually we can, because the CGA coarse grid aggregation, we can get about 2.6 times speed up. So actually that is an advantage. And this is based on we wanted the GPUs, okay? Now, so how about overall performance of a projection method? And this is different grid mesh. And we don't have this one, the reason why, because we are only using 2 NVIDIA V100 GPU. So you can see the best performance actually is based on from the Lady-Boltzmann method, because that is intrinsically, it's approximate by nature. So no wonder it's this one. And the general pressure equation, this is this one. And this is our previous work published in JCP. It's a dual time stepping artificial compressibility method. But you can see that, but depending on the divergent-free condition, this is 10 to the power minus 8, 10 to the power minus 12. If you relax a little bit, actually the performance is very compatible to the Lady-Boltzmann method. And this is with our previous serial code. Here we use a conjugate gradient to solve the pressure Poisson equation. Compare this one, we can get about per core, remember per core is 1,000 times speed up. And compared to general pressure equations, still we can get 3 times speed up. But however, Lady-Boltzmann, although it's very efficient, but however, the memory requirement is quite big. So now, so this is, we have tested, we are using a turbulent lead-driven cavity flow. And so this is the mean flow. We have 2 grids, the long uniform mesh, 192 cube, 256 cube, 512 cube. So we can see this is the mean velocity distribution and the turbulent intensity and the shear stress. And seems to be quite okay. And also we recently we have modified our program to include the immense boundary method that we have developed many years ago. And we put a sphere there. And this is a quite low Reynolds. The agreement is quite good. And we also have a moving object problem. So this is the typical benchmark. And we have a sphere falling down at 3 different Reynolds numbers. And we have a measurements. And the agreement with the measurement is quite compatible. But the solver itself, it's just from CPU to GPU. And the methodology is the same. So no wonder the agreement is good. So now we too have fluid structure interaction to sphere. So we can see we have a drafting because the sphere falling down, and there's a produce a low pressure region here, low pressure here. So this one will accelerate, they kiss each other, then they will be kissing and traveling. That is tumbling. Okay, the mesh I'm using here, remember that each sphere I have 85 cube mesh to model that. So altogether, I have 4 billion of mesh altogether. Okay, and the GPU is that is quite easy to be done because the memory GPU is quite big. Okay, so now, so again, I have 3 spheres coming down. Okay, the interaction is more complex. So if you have more than 5, it's very difficult to track, like a COVID, you know. One get infected, you can track them. More than 1,000, you cannot track them anymore. Okay. So now we have 64 spheres settled in a closed container. You can see that the pattern is very complex. You know, to be honest, I don't know whether they are true or not. But I asked my student to use 1,000, but he's struggling with that. Okay, but basically they can be done anyway. But I can, because you have more particles, the resolution actually reduces. But however, remember our previous test cases of single sphere falling down. 21 actually produce still quite decent results compared to the measurements. Okay, that is I catch up of time, so my time is finished. So we have implemented projection method and pressure evolution equation. We have demonstrated the possibility based on this one, and we also applied to that with fluid structure interaction with immense boundary methods. Done. Thank you for your attention. Thank you.